So here we are. This is worksheet number 6. We are making progress and we're doing symbolic language. It's a really exciting time. So I don't think that this is too hard, but there is a bit of an art to converting natural language into symbolic language. So that's what we're going to work on today. And a lot of this is going to be focused on quantifiers and some keywords that are going to give us a hint about what quantifiers to use. So we'll just jump right into it. Number 1 says there is a natural number greater than 2 that is not the sum of 2 primes. So let's think about that. That means there is some whole number that you can't take any 2 primes and add them together to make that number. So, for example, it's not going to be 12 because 7 plus 5 is 12, and 7 and 5 are both prime. So 12 wouldn't be an example of that, even though it is a natural number greater than 2. But now let's just work on writing this out. So first we need to establish the first variable, or our first number, which is going to be some natural number. And the question we need to ask ourselves is this: we have 2 quantifiers that we've learned about. We have this, which means there exists, our backwards e, and we have for all. Are we saying that there exists a natural number greater than 2, or that all natural numbers greater than 2? And if we look at the wording of this, there is a natural number. So there only has to be 1 for this to be true, which means we're in the realm of there exists. Now I'm going to get rid of all this. And so now we could say there exists some natural number, and we could call it n just because it's going to be in the set of natural numbers. So it might just be easier. In the set of natural numbers, and it's not any natural number. There's a caveat here that it's greater than 2. So it's going to be n greater than 2. Okay, that's the first part of our statement. And then what are we saying about it? This n is not just any n, it's particular. It's not the sum of 2 primes. Okay, so how do we say that it's not the sum of 2 primes? We kind of want to say that n is not equal to, let's say, like p1 plus p2. That's what we want to say. And now the last part of this is to say that we have to say what p1 and p2 are, because right now they're not defined. They could be anything. They could be colors. They could be pi and the square root of 2. They don't have to be rational. They could be negative. So just because I called them p1 and p2, it doesn't make them prime. We have to establish them as prime. So we have to say that p1 comma p2 are in the set of big P, which is the prime number set. And now we need to ask ourselves what quantifier goes on p1 and p2. Is it for specific p1 and p2, or for all p1 and p2, for all prime numbers? So I'm going to tell you the answer and then I'll explain it. So the answer here is that it's going to be for all primes. Had we said this instead, had we said that for specific primes n does not equal that, then actually we could just say that p1 and p2 might be like 2 and 3, because those are both prime numbers. And now the only thing that n can't be is 2 plus 3. It just can't be 5. But now n could equal 12. And even though 12 equals 5 plus 7, that doesn't matter, because those are not the 2 primes that we just kind of arbitrarily chose. I hope I'm being clear, but basically this kind of shows that there's a necessity for this to be all primes. And if I were writing this myself, I would actually take this and put it right here, just because it's kind of just better form to define your variables before you use them. Like here we said we used p1 and p2 in this inequality before defining what they are. So I think it's easier to think about it in the way I wrote it, which is why I wrote it the way I did. But maybe if I were doing a homework or something, I would realize this and I would flip the order. I'd erase and flip the order, which is why we use a pencil and not a pen, because we could erase pencil. That was a joke because I'm doing this on a computer. Hopefully some of you found that funny. Okay, so now we need to, do we have to negate it? Yeah, okay. Symbolic language, we're gonna negate now. So negating is super easy. And I'm gonna like pretend that this is over here for the negation. So you'll see how I kind of flip the order around when I negate this. Why is negating super easy? We're just gonna go stepwise and flip signs here. And the thing to remember with negation is you're never changing the universe that a variable exists in. So the natural number is still gonna exist in the world of natural numbers greater than 2. And the primes are still gonna be prime. They're not gonna be not prime anymore. So that stuff is never gonna change when you negate. The things that change are these quantifiers. The alls become exists, the exists become all, the equals become not equals, greater than becomes less than becomes greater than, or greater than or equal to, stuff like that. So this should be pretty easy. For all n, for all variables that are natural numbers bigger than 2, you guys should be able to do this for me almost. And now I'm gonna negate this part of the statement now, just because I like this order better. There exists P1 and P2. And you notice how I don't need to put an exists for both of them. It kind of just applies to everything in here. Exists a P1 and there exists a P2 in the world of the primes. So there are 2 specific primes such that n equals P1 plus P2. And now we're going to talk about what this means, why this is a negation on an intuitive level. I think you could see how I flip signs. I flip this sign, I flip that sign, I made the not equal to an equal. Now let's talk about what this means. This means that for every natural number bigger than 2, so basically every number from 3 to infinity, there exists specific primes that add up to that number. Okay, so now let's try to assess the truth value of this statement. So this statement is saying that there's some natural number that you can't add any primes together to make. And this is true. And the way you could prove this is you only need to find one example. We're saying there exists, so you just need to find an example of where it's true. And an example is n equals 3. And I think n equals 13 is also an example, because there are no 2 primes that add up to be 3. And that is largely because primes have to be greater than 1. The number 1 is not a prime. And so the only ways to make 3 with positive numbers is 2 plus 1, you have 3 plus 0, which is not strictly positive. And that's it. So there's no way to construct, there's no way to add 2 numbers to make 3 where both of those components are prime. So now I just want to do a brief aside and talk about when could we use examples to prove something. And this is something I talked with my group in last class, and I think that it's very useful. So when we start a statement with there exists, and we're trying to show that there is some value such that a bunch of conditions hold. In this case, we have this condition. If we want to show that there exists a number, all we have to do is prove it with an example. That's the easiest way to prove this. So here we just found an example, n equals 3, and that proves it. That's it. Now, if you say for all, it's always true, then you can disprove it with an example, but you cannot prove it with an example. Meaning, let's take it away from math for a second and say, let's say I think all trees are at least 10 feet tall. All the trees in the world are at least 10 feet tall. You can't prove that by showing me a 12-foot tree or I can't prove that to you by showing you a 12-foot tree, because that's not all the trees, that's just one. But you could disprove it with a smaller tree. You could say, look, here's a 6-foot tree. That disproves your claim. So when you make an all statement, like this negation, you could disprove with an example, and we call that a counterexample. And when you make a there exists statement, you can prove it with an example. Hopefully that's clear. I'm going to move on to the second one. I was a bit messy on that one, so try to improve. Cool. See how you could erase pencil? All right. Number 2, there is a prime. Here we have that same language. There is a natural number. There is a prime. We're talking about there exists. There is at least one. There is a prime that is one more. So let's just declare the prime. This should be second nature. There's a prime in the set of primes. You don't need to call it P. You could call it whatever you want. There's a prime that is one more than a multiple of 4 and is also a sum of 2 squares. Okay, this is a good one. So there's a lot of correct ways to write this. And when I was first going through it, I came up with a very different answer than the professor did, and I like the way she wrote it better. But we're going to construct it kind of in a roundabout way. So what does it mean that it's one more than a multiple of 4? It means that if you take like 4x and then you add 1, because it's one more than 4x, then you get p. So it's like p equals 4x plus 1, and x has to be some integer. Let's just say int. And this is our symbol for and. It's also the sum of 2 squares. So like a squared, that's an ugly a, plus b squared is also equal to p. Wicked. All right, so all we need to do now is we have this setup. Now we just need to write this in a way that is kosher. And so we need to declare what x is and what a and b are. And it actually happens to be that all of these just have to be integers. And the a squared and the b squareds, when you square an integer, it's going to be a positive number. So you're almost tempted to say that they have to be natural numbers, but they actually could be integers because of that property that when you square them, they become positive. So you could have like a equals -2 and b equals -3, and then you're going to end up with 4 plus 9 equals 13. And 13 is actually an answer to this problem, I think. 4 times 3, yeah, that works. And we're going to see why integer. Okay, so here's how we're actually going to write this. So there's a prime in the set of P. And now what I want to do, like if any of you code in Java, you tend to like declare all your variables at the beginning before you use them. So we could just say like, and here we're saying there exists, because it's not like x just has to be one number. It doesn't have to be every number. And the same with a and b. It's the sum of 2 squares. It doesn't have to be the sum of every 2 squares that you could come up with. That would be crazy. So there exists an x, an a, and a b. And what set are they in? The integers. Yay! Okay. X, A, and B, such that we start with P. P equals 4x plus 1 and P equals a squared plus b squared. And before I negate it, let's just talk for a sec, and we'll actually prove this with an example. Again, we have an exists statement, so we could prove it with an example. There is a prime number that satisfies both of these equations. So it's got to be prime. It's got to be one more than a multiple of 4. An easy way of thinking of that is you have to subtract 1 and then it has to be divisible by 4. So like I'll just bury the lead here, not bury the lead, I'll just tell you 13 is an answer for this. If you subtract 1 from 13 you get 12. 12 is a multiple of 4, so that satisfies this part. And 13 is prime, that's also important. And 13 is also a squared plus b squared if you assign 2 and 3 to a and b. 2 squared plus 3 squared is 13, so that's an answer. So it satisfies everything. And for an and statement, it has to satisfy both of these things to be true. It can't just be one. So now let's negate it. And to negate it, we're going to flip this sign for all the primes. So whatever we're about to say has to be true for every single prime. Hint, it's not going to be. And now for all xab, still integers, keeping the universe intact. Now this is the tricky part. Here we're going to have to flip a few things. Here we make equals into not equals, equals into not equals, and the and flips to an or. So p is not 4x plus 1, or p is not a squared plus b squared. Hopefully none of you are planning on screenshotting this ugly mess. Okay, so that's our negation. And this is saying that for every prime and for every x, a, and b, this is not true. These statements are not true. At least one of them isn't true. And a counterexample is our proof over here. It's number 13. 13 is a prime. It's also... And we could assign x to be 3, a to be 2, b to be 3, and these are both true, actually. We only need one of them to be true, but they turn out to both be true, and so that statement falls flat. So that is number 2. Check out this momentum that we have. And I'm actually going to skip number 3 because I really don't think it's so necessary. I think everything that we're going to get out of number 4, you'll be able to do number 3 pretty easily if you're able to do number 4. Okay, here we have this there is, and we already know that there is code for existence. There exists a natural number s. Here we actually got the variable labels. Like here we're going to call this one s, and we say that it's a natural number. There's a natural number s. Oopsies. So here we have a natural number s. Notice I'm writing this even before I read the rest of the problem. I don't even care. Like once I see this, I already know how I'm starting. There exists a natural number s such that for any, every, all, they all mean the same thing. This guy right here. For any natural number n, so n is a natural number. And now I'm going to guess we're going to have some sort of qualifying statement. S is the product of n with itself. And there was some confusion in my class about what itself was referring to. Itself is referring to n. So basically n times n. So the condition is that s equals n times n. And if any of you guys are math aficionados, you might like to call this n squared. So this is what the statement's saying. There's some natural number that is the square of another natural number, and that other natural number could be anything. We could change it and it'll still be true. That's a crazy statement. That is actually like patently insane. So let's just like throw out a funny example here. Like let's say we want s to be 4 because we know 4 is a square number. So that means that s has to be, s is 4. Did I say n? S has to be 4. S is 4, which means n has to be 2. Yeah, because natural numbers can't be negative, so it can't be negative 2. So n has to be 2. But we said that this is true for any value of n. So now if we change n to 3, it still has to be true, and it's no longer true. So now let's just negate it real quick. This is going to be really easy. For every s in n, there exists an n that's a natural number such that s does not equal n squared. There we go. Okay, and this negation is saying that for every natural number s, there exists some natural number such that s is never the square of n. What does that mean? For every s in n, for every natural number, there's some n. Let's maybe even start with this. There's some n that for every natural number s, this is not true. Oh, that can't be right. Whatever you take, the problem with this statement is that whatever you choose to be your value of n, there exists. It's got to be at least one specific n. Whatever you choose to be n, you could always square n, and it's still going to be a natural number, which means s is still going to cover it, because we said for every s in n. So for every natural number is what this is basically saying. Here we're saying for a specific natural number. Here we're saying for every natural number. Okay, so now let's go about proving it. So this statement is true. And this proof is probably like the most challenging part of the worksheet. And yeah, let's walk through this. So we have s equals n squared. I'm going to erase the negation just to give myself a little bit more room. Wicked. Okay. So we have s equals n squared. And that's actually like, we just assigned a value to s. S equals n squared. But we also said that s has to be that value. It has to be n squared. It has to be what it is for any value of n. So basically the statement has to be true when n is 3 and when n is 4. So like if we say s equals 3 squared and s equals 4 squared, both of these have to be true for our statement above to be true. There's some s such that for every single n, s equals n squared. Hopefully if you realize that this statement is crazy, that means you understand the statement. So hopefully you guys understand that this statement makes no sense. So there has to be some s that is equal to 3 squared and 4 squared. And that means that would imply that 9 equals 16. And that's not true. So our statement's false. And you could think of this as a proof by contradiction. I didn't exactly phrase it that way. But I think you could think of this as a proof by contradiction. False. Okay, and I'm just going to quickly go through the proof that the professor gave us, because I think this is a good proof. A little more elegant than what I just showed you. So she says that the statement is true for n, and it's also true for n plus 1, which is true. Like we were just talking about how n could be 3 or n could be 4. You could think of it as n and n plus 1. So we have s equals n squared, and it also equals n plus 1 squared. This is, I don't know if you need to do this much work for the proof. I think that what I just showed you with 3 and 4 is probably sufficient, but this is cool, and it's going to lead us to to a nice contradiction. So if we just unravel this n plus 1 squared, we get n squared plus 2n plus 1. And in order to maintain the equality of n squared and n squared plus 2n plus 1, we're going to subtract out the n squareds, and we end up with this 2n plus 1 is equal to 0. You do need a little bit of algebra in this course, but it's really not that much. And if we subtract 1 from both sides and then divide by 2, we get n equals -1/2. And you may be asking yourself, what's wrong with that? That seems like a great solution. In my algebra class, this would be the answer. But here, it is the contradiction, because we said over here that n has to be a natural number. And here we concluded that in order to maintain the truth of this statement, n cannot be a natural number. It has to be this fraction, -1/2. So therefore, we have a contradiction, and the statement's not true. Alrighty, that was it for Worksheet 6. Hopefully this was helpful. Have a good day.